Hi guys. We are gonna do 5-4 today. We're gonna skip a lot of slides, so if you're following along with the ones we uploaded, just keep up because we're gonna skip quite a bit of stuff. So just a heads up there. We're gonna start with the warm-up just to make sure we know how to do this because there's a lot of this on the quiz that's gonna happen in a couple weeks, so we just need to make sure we're good at it. So this says the number of hours per week American adults spend on home computers is normally distributed, which means it's got the bell-shaped curve, with a mean of 5 hours, so mean is mu, and a standard deviation of 1, so that's your baby sigma. Find the probability that the hours spent on the home computer by a selected adult is more than 7.5 hours, which is going to be your x. So in order to use your table, you need your z-score, which is x minus mu divided by baby sigma. So our z-score is x, which is 7.5, minus the mean, which is 5, divided by the baby sigma, which is 1. So on top, you take the 7.5, subtract the 5, which is 2.5, divided by 1 is still 2.5. So 2.5 is your z-score. Now, a couple things. First of all, your x was bigger than your mean, so your z-score was positive because you are above mean. And 2.5 is a pretty big z-score because anything, remember, 3.5 is the maximum. That's anything outside of 3.5 standard deviations is highly, highly, highly unusual. So 2.5 is still pretty big. So our area to the left, which is what the chart tells us, is probably going to be relatively large. So on your chart, you're going to find, be on your positive side, you're going to find 2 along the left and 2.5 along the left. Since there was not another digit after the decimal place, you're just going to do the 0 column, which is the first one. So 0.9938, which is pretty big, which is what we were expecting. So 0.9938 was the area. However, to remember the chart gives you the area to the left, and that says more than. More than indicates that we need the area to the right. So the fact that it was more than means you have to take 1 and subtract the area that you found on your chart. So 1 minus 0.9938 gives us 0.0062, which is tiny, which makes sense because 2.5 was a pretty big standard deviation or pretty big z-score. So anything to the right of that, there's not going to be a whole lot to the right of a 2.5 z-score. So 0.0062 is a small number to the right, and that's what we would have expected. Okay? We're doing the central limit theorem today. We're kind of getting to the point in the year where stats get super complicated, and since we aren't at school and it's super complicated, I'm going to try to kind of dumb it down, I guess, in a sense. So we're going to skip a lot of stuff because I'm just going to teach you how to do it more so than the why that I would normally teach you. So that's why we're going to skip a lot of the steps today, okay? For the central limit theorem, so I don't think you really need to know any of this. So just kind of skip through that. You can read through it if you want, but it's not super important. This is what we're going to focus on mainly. So the mean is mu x bar of the sampling distribution. So instead of looking at entire populations, we're looking at samples again. So the mean, the way we write that is mu x bar because it's of the sample, not of the entire thing. However, when we are talking about the central limit theorem, the mean of the sample is the same as the population mean. So whatever they give you as the mean is the same mean you're going to identify as your sample one. The only thing you have to calculate is the standard error of the mean, which this is what you're going to do to find the standard error. Okay, so baby sigma x bar is the standard error of the mean. You have to take baby sigma, which is your standard deviation, and divide it by the square root of n. If you remember way back to the beginning of the semester, n is your sample size. So you're going to take your standard deviation divided by the square root of your sample size to get what's called the standard error of the mean. Okay? We're skipping this next couple slides completely because it gets too much. So just skip through it, skip through this chart. We're going to go to the slide that says central limit theorem. Okay? So here there are two criteria that can be met in order for the central limit theorem to apply. Okay, one or the other, it doesn't have to be both. The first one is that your sample size has to be greater than 30. Okay, so your n has to be greater than 30, then this criteria fits these things down here. Okay, if it's not greater than 30, then it has to be normally distributed. Okay, so it either has to say that the data is normally distributed, meaning it fits that bell-shaped curve. If it's not normally distributed, then your sample size has to be bigger than 30. Those are the one or the other has to be met. If one or the other works, then you find the mean by just identifying the mean of the entire population. So mu x bar and mu are equal to each other. Variance is baby sigma squared, because that's your variance, divided by n. Standard deviation is the same as the standard error, which is what we just talked about, baby sigma divided by the square root of n. Okay, so we're just going to go through an example. I know it's a lot of new words and it's complicated, but the math isn't that hard, so just pay attention. The phone bills for residents of the Cincinnati have a mean of 64, so that's your mu. Just like always, just go through and identify what you know and then figure out what else you need to answer. The standard deviation of 9, so that's your baby sigma. Random samples of 36 phone bills, so your sample size, n, is 36, are drawn from the population. Find the mean and the standard error of the mean. So, first of all, nothing about this says it's normally distributed. If it was normally distributed, it would say it's normally distributed. It doesn't say that, but my sample size is 36. And 36 is bigger than 30, so we can still do it this way because the sample size is bigger. So all you have to do is say mu x bar, which is my population my population mean, is equal to the mean of the entire thing, which was 64. All I did was repeat the mean that they gave me. Now, standard error of the mean is baby sigma x bar, which you find by taking the normal baby sigma and dividing it by the square root of n. So my normal baby sigma I already know was 9, and I'm dividing that by the square root of my sample size, which was 36. So you're just taking 9 and dividing it by the square root of 36. Well, the square root of 36 is 6, so you're just taking 9 and dividing it by 6, and you get 1.5. So 64 is the mu x bar, 1.5 is baby sigma x bar, which is the standard error of the mean. Standard error of the mean is baby sigma x bar, which is the only thing you actually had to calculate. Okay, and that's it. So we just identified this mean, standard deviation, sample size. So mu x bar was 64, baby sigma x bar ended up being 1.5, and that's all you had to do. Now, suppose random sample sizes of 100 are drawn from the population. So the mean didn't change. The baby sigma didn't change from this previous one. So my mu was 64, my baby sigma was 9. That's still the same. So mu is 64, baby sigma was 9. The only thing that changed was my n. So instead of taking 9 and dividing it by 36, which is the square root of the sample size before, I'm now going to take 9 and divide it by the square root of 100 because my n changed. So the mean didn't change, so my mu didn't change. My n did change, so then my baby sigma x bar went from 1.5 down to 0.9 because my sample size was bigger. So I was dividing by a larger number. Okay. The heights of fully grown white oak trees are normally distributed. The fact that it says normally distributed tells you that it doesn't matter what your sample size is. Okay, as long as it's normally distributed, you can have as few samples as you need. Okay, the mean is 90, so that's your mu. Standard deviation is 3.5, none of that's changed. Random sample sizes of 4 are drawn. Yes, that's small, but it doesn't matter because it's already said it's normally distributed. Find the mean and the standard error of the mean. So the mean, mu x bar, is the same as the mean that was given to you, which was 90. Done. Then baby sigma x bar is the only thing you actually have to calculate. Take your baby sigma, which was 3.5, and you divide it by the square root of your sample size. My sample size was 4, so I'm taking 3.5 and dividing it by the square root of 4, which was 1.75. Done. It's not hard, you just have to know what they're asking. So if you see standard error of the mean, that's when you have to do this whole baby sigma divided by the square root of n. Okay, this is just same thing. One more. The diameters of the white oak trees are normally distributed, so it doesn't matter what your sample size is because it's normally distributed. With a mean, mu, 3.5 and a standard deviation, baby sigma of 0.2, random sample sizes of 16 n are drawn from this population, and the mean of the sample is determined. Find the mean and the standard error of the mean. Standard error means that's your baby sigma divided by the square root of n. So your mu x bar is the same as the mu they gave you, so 3.5. Your baby sigma x bar, baby sigma x bar, you're going to find by taking baby sigma, 0.2, and dividing it by the square root of n, which is the square root of 16. So you're going to take 0.2 and divide it by 4. Okay, that's it. The mean was the same as the mean up there. Baby sigma x bar, you did the work and got 0.05. All right, 5-4 worksheet, you're going to do 5 through 8 all. If you have any questions, let me know. Bye, guys.